Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Question 29 states that a nuclear power plant is 25% efficient, meaning that only 25% of the power it generates goes into producing electricity. The remaining 75% is wasted as heat. If the plant generates 8 times 10 to the 8 watts of electric power, and then the energy released from each fission is 2.0 times 10 to the 2 MeV, how many kilograms of uranium-235 are fissioned per year? So we are dealing with uranium-235, so let's make that clear. We're given a power and amount of energy, so we know that if we're given a power, we will be able to find the mass of uranium, which is our goal here. So based on each of these, we can figure this out. So I have E over N here just to represent the energy per fission. So N would just be the number of fissions, which would represent the number of atoms present, right? So first thing we'll do is we want to find how much energy is produced. So the total amount of energy, we can base it to be on the power multiplied by time. And if it does state that I believe it says somewhere per year, right? So we're looking for this amount of power is for a given year. So if we look at our value here, so we have 8 times 10 to the 8 watts. We can also say watt is a joule per second. And we're looking over the time frame of a year. We know that in 1 year, we can look this up, or if you know off the top of your head, good for you. But I had to look it up. There are 3.156 times 10 to the 7 seconds per year. So we can cancel out units of seconds. And so, and if we're multiplying by 1 year, just to represent that's the time frame we're dealing with, the amount of power in that 1 year in total was 2.52 times 10 to the 16 joules. So this is the amount of energy that is generated or is usable. Then the energy, I'll say total for the year. Well, again, in the question, it does state that this plant is only 25% efficient. So if this is the usable energy, then the total energy produced is this energy value divided by 0.25, or basically multiplied by 0.25, sorry, because that's the measure of the efficiency. So the total amount of energy generated would be 1.01 times 10 to the 17 joules. Great, so now if we want to find the mass, well, one thing we do know is that if we look at this ratio, if we have the total energy produced over the energy per fission, then this value will produce the number of atoms that we have. But if we have the number of atoms for a given nuclei, which we know what nuclei we're dealing with, we also know the relationship, the number of atoms present in a sample is equal to the mass of the sample over big M, which I'm calling the molar mass, multiplied by Avogadro's number, so the number of atoms per mole. So using these two relationships, we can solve for the mass and then plug in from there. So if we take a look at this equation here, we can rearrange this such that the mass of the sample we're looking at is equivalent to the number of atoms present multiplied by the molar mass divided by Avogadro's number. This value for the number of atoms will replace with this ratio. So the total energy that we want to that will be produced over the ratio of energy per fission. So this is the total energy on our numerator multiplied by our molar mass divided by our energy per fission multiplied by Avogadro's number. So again, remember this relationship is based on, it's simply the chemistry, but we use it multiple times to determine the number of atoms. So we have all of these terms now, and so we can go from here. So our total energy that we know is 1.01 times 10 to the 17 joules, multiplied by the molar mass of uranium-235, which is 235.044, which we can look up. You see that's grams per mole. This whole term divided by, well, now we have a little bit of a unit issue, 2.0 times 10 to the 2 MeV per fission or per nuclei, which is what we want. However, we don't want MeV, so we either convert the numerator from joules to MeV or vice versa. So we have 1.6 times 10 to the negative 13 joules per MeV to convert our units to joules, and multiply that by Avogadro's number of 6.022, oh, I might run out of room, times 10 to the 23, sorry about that. That would be atoms, or I'll say fissions, per mole. Sorry for this mess. Double checking our units, joules cancels out joules, MeV cancels out MeV, number of fissions cancels out number of fissions, moles per moles, and we are left with grams. So by solving this, we find that the number of grams is 100, well, I'll just write it all out, a lot, 1,231,911 grams. It's easier to put it in kilograms, and given that we're given two significant figures, our final answer would be 1,200 kilograms. So there you go. So based on initial given power, we can find the amount of energy produced by this reactor. Based on efficiency, we can find how much is actually produced. So this is the yield amount, so how much power is usable. However, we want total energy produced. And based on a little bit of chemistry, given a molar mass and the mass that we're looking for, we can find the number of atoms or number of fissions based on the energy ratio relationship, and we can just rearrange that to solve for mass. So there you go.